Ray is a popular distributed compute framework for running AI ML workloads, training them, doing data processing, all sorts of things that are important to AI and ML as a whole. The trick about it is that it comes with no security out of the box. And so you, as a Ray infrastructure administrator, user, have to really think about security. And today we're going to talk about what it takes to lock down Ray and harden it in your GKE cluster.
Welcome to Container Bytes. I'm Mofi,
My name is Bill Burnson. I am a security engineer on GKE Security.
and let's talk about it.
So today we'll be talking about Ray. What is Ray? Ray is an open source unified compute framework that makes it easy to scale AI and Python workloads, from reinforcement learning to deep learning to tuning and model serving. It has grown in popularity in recent years, and we're seeing broad adoption of it across the industry.
So, why Ray on GKE? Traditional Ray deployments on virtual machines have limitations when it comes to scalability, resource efficiency, and infrastructure manageability. One alternative is to leverage the power and flexibility of Kubernetes and deploy Ray on GKE with KubeRay. With GKE, you get the flexibility, scalability, and performance benefits of Kubernetes as a managed solution. And as we will see later in the video, how GKE allows for building a stronger security posture for building an ML platform using Ray.
So today we're here to talk about Ray and specifically Ray security. A few months back, a research team put out a vulnerability known as Shadow Ray. This had a series of CVEs, four of which the Ray team fixed. A fifth they noted was not a vulnerability is in their estimation. This is actually a core product feature of Ray, and something that they call out in their blog post is that security for a Ray cluster must be implemented outside of the Ray cluster itself. With GKE, you have access to a number of powerful security tools that allow you to lock down access to your Ray clusters and secure your AI ML workloads. Ray is a powerful and flexible tool. You can use it for many aspects of AI and ML workloads. Here we'll explore an example training environment where you have multiple users, researchers, who will be running each of their own Ray clusters, all on one GKE cluster. The aspects of this architecture of this use case that we'll be looking at today. How do you add identity, authentication, authorization to those researchers accessing their clusters? How do you add network and perimeter firewall controls to make sure the right people get to the right places? And then how do you also worry about and protect against denial of service attacks, noisy neighbors, resource quotas, and a few other bonus hardening advice when it comes to things like container escapes, breakouts, kernel level or OS level hardening. Also, other controls that you may have at your GCP organizational or project level that you can implement in order to make the most secure Ray environment on GKE.
We start with Kubernetes namespaces. Namespaces are lightweight logical separation of Kubernetes resources. In our setup, every researcher gets their own Ray cluster, and each of those Ray clusters live in a separate namespace. But Kubernetes namespaces by itself is not a strong security boundary. Namespace lays the foundation for the rest of our Kubernetes security control.
Next up, we're going to talk about role-based access controls, or RBAC. RBAC is Kubernetes' native identity and access management solution. There are three primary components to Kubernetes RBAC. The first is identity. Identities can be users, groups, or service accounts. Identities are what we grant privileges to via roles. Roles, which we grant to our identities, are logical least privilege groupings of permissions. Finally, we have role bindings. Role bindings are the glue that bind a role to an identity, a user, a group, a service account. Set your Ray clusters to run as service accounts that have no role bindings. They shouldn't need any permissions to interact with the Kubernetes control plane.
You can enable Kubernetes resource quota to prevent resource exhaustion, denial of service, and accidental overspend. You should set default quota for each of the namespaces. And you can set these resource limits for any types of resources that Ray would be using, like CPUs, memory, GPUs, and TPUs.
You should set pod security contexts on your runnable Kubernetes objects. These include things like pods, deployments, and potentially jobs. Security context controls how your container runs on the Linux operating system. It may set the user group ID, control whether or not it runs as root. Other examples is it may restrict syscalls or add SE Linux or AppArmor. These are all good ways to ensure that your container runs as securely as possible on the nodes in your cluster.
If your workload needs access to other GCP resources, you can use Workload Identity Federation to do that via standard IAM. To make this simpler, we recently added a simplified syntax that allows directly binding a pod's workload identity in IAM.
With Identity Aware Proxy, you can add Google standard authentication and authorization to gate access to your Ray clusters and workloads. When you use Cloud IAP, first it authenticates you using the standard Google sign in page. Next, it moves on to authorization. Authorization is controlled by standard GCP IAM. Once you've been authenticated and authorized, you will have access to your Ray cluster.
Pod security standards enforce a certain level of security guardrail. You should set pod security standards on all Kubernetes namespaces. Kubernetes built-in pod security standards comes in three flavors: privileged, baseline, and restricted. All Ray clusters should work with baseline and can be upgraded to restricted. This can help prevent common insecure misconfiguration such as host path volume mounts.
Containers are not a strong security boundary. Container to node breakouts, escapes are a common concern amongst Kubernetes workloads. GKE Sandbox protects against these by re implementing the Linux kernel API in user space. GKE Sandbox acts as an intermediary between your untrusted workloads and the Linux operating system kernel, making sure that any vulnerabilities in the Linux kernel do not lead to a container breakout. GKE Sandbox must be enabled on each node where you'd like to use it, and then it can be set on each pod or deployment in your fleet. Particularly relevant for AIML workloads and Ray clusters, GPU support is now in public preview.
By default, GKE Autopilot already applies a lot of cluster hardening best practices, but there are some additional ways to lock down the cluster. The Ray API can be further secured by removing access from the internet by using private nodes. Generally follow best practices, like CIS benchmarks to maintain cluster security.
Organization policy allows you to scale your security from a single GKE cluster with multiple Ray clusters and users running on it to a globally distributed AIML training ecosystem across multiple GKE clusters and teams. Organization policy lets you set high level guidelines and guardrails around which GCP services and settings can be used. Custom org policy allows you to become even more granular, setting specific policies around which aspects of GKE security must be enforced when new clusters are created.
In this video, we saw a number of ways that we can improve the security posture of our Ray cluster running on GKE. Links to a blog post covering everything we talked about today and additional further readings will be in the description below. If you have any questions about how to secure your Ray cluster or other workloads on Kubernetes, let us know in the comments.